Greetings everybody. Let's take a look at circulation and flux in two dimensions. When we talk about flux, we're really talking about the amount of our vector field that's actually passing through a curve or a surface that we're interested in. And so we've got at each point in the plane, we've got our vector field, we've got these vectors attached to it. We're just coming up with this curve, whatever curve we happen to want, and we're looking at how much of our vector field is going to be kind of pushing through that curve or coming through that curve at each point. Now, how we go about doing that is we imagine at each point on this curve we've got our tangent vector where we're headed off in this direction. We've got the normal to the curve coming off that's going to be perpendicular to our unit tangent vector, and then to that point we've got our field vector that's pointing off in some maybe arbitrary direction from there. Well, what we want to look at is the component of our field vector that's actually in the normal direction, or it's the opposite of the normal direction to the curve. So we're really looking at this projection here for that field vector in the direction of either the opposite of the normal vector or in the direction of the normal vector, depending on whether we want to look at the flux coming in through the curve or passing out of the curve. And so how we actually end up doing that is really just the integral over the curve itself of our force vector dotted with n hat being the unit normal vector to the curve that we're interested in. So the unit normal either facing in or the unit normal facing out, and ds then is just our usual arc length form. And so again, kind of reinforcing this fact that we're just looking at these projections. Remember that the dot product is just the magnitude of that projection. And so when we're taking this dot product, our formula for that was just going to be v dot w over the inner product of v with itself in the direction of v. And so when v happens to be a unit vector already, this denominator is 1, and so we just get the dot product in the direction of v itself. So what the integral then does is just perform a sum of all of those tiny projections at each point that we've got really along the curve. So let's look at an example maybe of how we go about actually computing one of these things. And so suppose we want to calculate the flux of this vector field f, x over e to the x squared plus y squared, y over e to the x squared plus y squared, across a parameterized curve that's really just a unit circle parameterized counterclockwise with a radius of a. And we want the flux to the right of the direction of travel. So we're going counterclockwise, and so we want the flux facing out, and so we want the normal vector that's facing outward from the curve. Well, how do we calculate that? Well, we've got our parameterization for the curve, a cosine and a sine. A is just going to be some positive real number. So we want kind of graphically again, we want the direction that we're tracing the curve out is counterclockwise. We want the unit normal facing outward since we want the direction to the right of how we're tracing out to the curve. And so kind of one nice thing about this is because it's a special case of a circle, when we kind of go back, it's pretty easy to see that the outward facing normal is really just going to be the same as the radius vector that's pointing out to the curve itself. And so however we make our calculations, our result geometrically should be just the same as the radius vector that's pointing out of the curve. So let's see if we can actually get there. Okay. So what we should get in the end, our unit normal is just cosine t sine t. Let's see if we can actually compute that and get that. Okay. So if we couldn't see that geometrically for what it was going to be, or we had a curve that where it wasn't quite going to be that obvious, what do? Well, we recall that the unit tangent vector is just going to be the normalized derivative of the position vector for the curve. So we've really just got r dot over the norm of r dot, and this was the same thing as dr ds if our curve was parameterized with respect to arc length. Well, when we took the derivative of that with respect to arc length, so the dt ds, that's where we got our curvature times our normal vector. And how can we kind of bring this back? Well, remember that dt by dt, the derivative of the unit tangent vector with respect to this arbitrary parameter was just going to be ds dt dt ds. And so ds dt, that was our arc length. Remember, where we got this was from our arc length function. We took the derivative of that. Fundamental theorem of calculus said that this was just going to be the derivative, or the norm of the derivative. And so what we kind of get from that is that if we take the derivative of the unit tangent vector with respect to any arbitrary parameter, it's going to be parallel to our unit normal vector. That this one is just a scalar function, the norm of r dot is a scalar function, kappa is, the curvature is just a scalar function, and so this is just going to be parallel to our unit normal. And we can really kind of use that. And so when we got the derivative of the unit tangent with respect to an arbitrary power, it's going to be parallel to the normal. And so computationally, do we have to really find the normal vector and can go through that? Well, not really. We can take a little bit of a shortcut and just take the derivative of the unit tangent vector with respect to our parameter and then just normalize from there. And so the vector we want, which is normal to the curve, then is either just our unit normal or the negative of our unit normal, depending on which direction of the flux that we are interested in calculating. So if we come back to our example, we've got our parameterized curve, a cosine t, a sine t. We take the derivative of that, so we get a minus a sine and an a cosine. Well, the length of that just reduces to a. So our unit tangent has the form r dot over the norm of r dot is just a negative sine cosine. So if we take the derivative of this with respect to our parameter t, we get minus cosine minus sine. Well, here we're in luck because this is already a unit vector. So we don't need to normalize because we are already a unit vector if we look at the length of that thing. And so the unit vector we want is either dt, so the derivative of the unit tangent with respect to time, or the opposite of it. And since we want the one that's facing outward, we do that calculation. We see that, oh, this is just going to be our cosine t, sine t, and that's how we choose our unit normal. So we want our unit normal just being our cosine t, sine t, which typically coming up with that calculation and making sure that we get the right n unit normal, that's usually our biggest step in doing any of these things. And so now calculating the flux, we've got our line integral over c of f dot n ds. Well, we've got ds being ds dt, so the length of r dot times dt, so that's a dt. Our unit normal was cosine t sine t. If we evaluate our vector field along that curve, we get a cosine t over e to the a squared, a sine t over e to the a squared. We simplify that, factor out our a and e to the a squared in the denominator, giving us this expression. Kind of putting all of that together into our integral, we get the integral from 0 to 2 pi. We've got our vector field f evaluated along the curve. We've got our unit normal that we calculated, and then we've got our ds. We put all of those together to get one integral, and just reduces to the integral from 0 to 2 pi of a dt, which just gives us a squared e to the negative a squared times 2 pi. And so there we've kind of introduced this notion of flux and shown an example of how you would actually go through and calculate those. We'll do maybe another one of those and talk about circulation in an upcoming video, and I will see you guys then.